Quantum chemistry. Okay, why are we talking about quantum chemistry and just what is it? Well, what's really interesting is that the macroscopic world, meaning the world around us, we see cars and trees and wind and all those sorts of things, the laws that govern this macroscopic world don't work when you start talking about the microscopic world. Microscopic world is the size of the electron. And then when you get to the size of the electron, my goodness, energetically impossible things happen. Not only with energy, but with position, with momentum. Nature behaves is very, very strange on that microscopic level. And that's the field of quantum mechanics or quantum chemistry. If you're a chemistry major, an entire course is devoted to quantum chemistry called physical chemistry. Okay, so we're just going to delve into this a little bit. One of the things to get us started is to give you an example of how properties change for very small objects. For example, here's magnesium in both of these bottles. This bottle contains magnesium strips, and you can see it's typical metal. It's nice and shiny. If you take the same magnesium strips and just chop them up into little tiny pieces, you get a powder. And look at that. It absorbs every single color. It doesn't reflect anything. So the properties of this material is very different than the properties of this. You can only explain this behavior through quantum mechanics. Quantum mechanics or quantum chemistry allow chemists to make some very complicated theoretical calculations. And these calculations allow us to determine reactivity and other chemical properties and predict them of a molecule without even doing the reactions. It's really powerful stuff. Another example of quantum chemistry is that different gases emit different colors. Let me show you how this works. Using this equipment, we can actually see the different colors being emitted from the atoms of an element. Check this out. They call this a discharge lamp. This lamp is filled with helium gas. Here's another discharge lamp, but it's filled with gaseous mercury atoms. Here's our power supply that we're going to use to ignite the lamps. And this is a diffraction grating that we're going to use to see the different colors being emitted from each lamp. Let's try the helium lamp first. Turn it on. So you can see the colors. Room lights. We have to turn the room lights off. Let's try it again. There we go. So these are the colors being emitted from gaseous helium atoms. Now the lamp made these atoms in a very high energy level. So what happens is that these very high energy helium atoms, they want to drop down to lower energies. And each time they drop down to a different lower energy, they emit a different color. Now let's check out the mercury lamp. Turn it off. Now with the mercury lamp, the atoms are different. So we should have different energy levels. So we should see different colors. Oh, nice. Check these colors out. So with gaseous mercury atoms, we see different colors because the energy levels are different. These excited mercury atoms drop to different lower energies and each time emit a different color. So here are some static images of the different colors. The gaseous helium atom energy levels are different than the gaseous mercury atom energy levels. Since the energy levels are different, we see different colors from these two different atoms. So different colors correspond to different energies. Now, Dr. Niels Bohr really got us started on explaining this. Now, his ideas aren't part of quantum mechanics. So different colors are different energies. For example, red is a higher. So different colors correspond to different energies. Now, Dr. Niels Bohr, he started so different colors correspond to different energies. And Dr. Niels Bohr really got quantum chemistry started. Now, his model of the atom is wrong. It doesn't agree with quantum chemistry. So different colors correspond to different energies. Now, Dr. Niels Bohr, he got us started. His ideas of the atom are wrong, but there's a lot of really useful terminology that he introduced. So I think it's important. So different colors correspond to different energies. Now, how could different atoms emit different colors? Well, they have different energy levels. And the Bohr model of the atom, while wrong, it's really useful in introducing some quantum chemistry concepts. So what does Bohr's model of the atom look like? Well, in the center of every atom is a nucleus. And it contains a very hard core, massive, in the center of every atom. So if you imagine an atom the size of a football field, the nucleus, the very center of the atom, is going to be the size of an orange on the 50-yard line. So here's my nucleus. And that nucleus contains positive protons and neutral neutrons. So most of an atom is empty space. But in this empty space is flying around negatively charged electrons. So most of an atom, so atoms are made up of pretty much empty space. And in this empty space are flying around negatively charged particles, electrons. So atoms are mostly empty space, and in this empty space are negatively charged particles called electrons. Now, these electrons, in the Bohr model of the atom, they flew in possible trajectories, possible orbits. So let's say this electron, it can travel in this orbit, or it can travel in this orbit, or it could travel in this orbit. Okay? And the farther out you go, that electron is going to have higher energy. So if that electron is way out here, and then it jumps to this lower orbit, it emits a color. Perhaps that color is green. What if that same electron maybe instead of jumping from, or that same electron could have jumped from that orbit all the way to this inner orbit. Then maybe it would emit blue. or that same electron could have jumped to the inner orbit. And in doing so, it emitted a blue light. So that's the idea behind different atoms having different energy levels. So since they have different energy levels, they have different So that's the idea behind the Bohr model of the atom. Each atom has these possible different orbits for its electrons. And these electrons just jump from one orbit to the other, and they emit different colors because their energy levels, their orbits, are different for different atoms, different elements. Okay, see if you can do better. Let's try, see if you can do better. So what does the Bohr model of the atom look like? He said in the very center, there's a nucleus. And that nucleus contains positive protons and neutral neutrons. And the rest of the atom is pretty much empty space. So pretty much imagine if an atom could be the size of a football field, if you could blow up an atom to the size of a football field, this nucleus will be the size of an orange on the 50-yard line. So atoms are pretty much empty space. What's contained in this empty space? Well, nothing, right? It's empty space. But that's where the electrons hang out. So electrons are the negatively charged particle. And these negatively charged particles, in the Bohr model of the atom, they can travel in orbits, in circles, around the nucleus. So let's say here's one orbit, here's another orbit, and maybe another orbit. So these orbits are the possible trajectories or where these electrons can be located. So notice the atom is still mostly empty space. So where do the colors come from? Say the electron has these different orbits. In this case, there's 3 orbits. 3 different trajectories that the electron can have. And notice orbit number 1 is the farthest out. So it's the highest energy orbit. And let's pretend that electron is in that highest energy orbit, and it's going to jump down to the next lowest energy orbit. So when it does that, it emits a color. In this case, let's say the color is green. But perhaps that same electron could have jumped to orbit number 3. Now that's a bigger energy difference. So now it emits a higher energy color, perhaps blue. Blue is a higher energy color than green. So this is the idea behind the Bohr model of the atom, that different elements have different orbits for their electrons. And these electrons jump from an outer orbit to an inner orbit, releasing energy in the form of colors. And since the energy levels are different for different elements, we see different colors from different elements. Quantum mechanics is very heavy on statistics, and there's a lot of math involved. In fact, there's a lot of differential equations. And when we set up these wave equations, they're called, there's only one atom that the equations of quantum mechanics can be solved for exactly. Isn't that interesting? With all of our supercomputers, there's only one atom that we can solve exactly, and that atom is hydrogen. The reason why is because there's only one electron. It's the simplest atom to solve. So these solutions are referred to as hydrogenic orbitals. And they're pictured below. So do you notice that the Bohr model is wrong? We don't see circles. We don't see orbits. Instead, we see what we call orbitals. They're these complex three-dimensional shapes. And 1s is the lowest energy, pictured here. And then the more shape you get a higher energy. So here's 2p orbitals, a little bit higher energy. We have d orbitals, even higher energy. So when boiled down, these solutions to the hydrogen atom are described using quantum numbers, and they follow rules as organized in this table. So understand this table, because the information contained in this table pretty much is our game plan in answering every single homework question. So let's start with the quantum number symbols. Symbols for the different quantum numbers are N, L, M sub L, and M sub S. So we have 4 quantum numbers. One of the main ideas behind quantum mechanics is that each electron in the atom has its own individual set of quantum numbers. And once you know these quantum numbers, you know what the energy is of that electron and the orbital that it exists in. This quantum number N, its description is the shell. So you'll hear that. And you'll also hear the name of it. The name is the principal quantum number. And what are its possible values? Well, N could be 1, 2, 3, 4, 5, just the whole numbers, and on up. Now we also need to know the letters for these different values. So if N is 1, that's capital K shell. If N is 2, L shell. M, N, O, P, it just gets alphabetical after that. Quantum number L is called the angular momentum quantum number. And its description is the subshell. So you might also refer to it as called the subshell. And what are its possible values? The angular momentum quantum number can go from 0 all the way up to the value of n minus 1. So we need to know the letters for L too. So L could be 0, 1, 2, 3, 4, 5, 6, on up. And what are the letters that correspond with those values? Are S, P, D, F, G, H, I. This gets alphabetical after that. Quantum number M sub L is known as the magnetic quantum number. And we use it to get the number of orbitals. So what are its possible values? Negative L all the way to positive L. And our last quantum number symbol is M sub S, and it's called the spin quantum number. And its description, when we start talking about line splitting, those lines that we saw in our movie for different colors from different elements, they're actually split. You can actually split them, and that's due to this quantum number, M sub S. So M sub S can either be positive 1/2 or negative 1/2. So let's see if we can use this table to answer some questions. How many subshells in the L shell? So we just need to get used to the terminology. Subshells, what quantum number is that? L. Capital L, what quantum number is that? N. Right? You can look at subshell, corresponds with L. Capital L refers to N. So, how many subshells in the L shell? Another way of asking this is how many different values can L be if N equals L, and L corresponds to the number 2. So using our table, we can see that L can only go from 0 all the way up to n minus 1. Well, that means 0 to 2 minus 1, just 1. So L can only be 0 or 1. Well, it's 2 values. So that'd be our answer. How many subshells in the O shell? Well, if it's O, that means N has to be what? If it's O, N has to be 5. So that means L can be what? 0 all the way up to 5 minus 1. So that means 0, 1, 2, 3, 4. And how many values is that? 5. How many atomic orbitals in the p subshell? So now how many orbitals? That means they're referring to m sub l, right? Because m sub l referred to the number of orbitals. In the p subshell, it's p. What does that mean? It's a small p. L is 1. So that means L equals 1. So m sub L, what do we say m sub L is according to our table? Negative L to positive L. Negative 1 all the way to positive 1. And these are all whole numbers. So negative 1, 0, 1 is what m sub L could be. So how many atomic orbitals are there? Count them up. 3. So try these. See if you can get the same answer as me. If the quantum number of an atomic orbital is 4, so if n equals 4, what are the possible values of L? Well, L equals 0 all the way to 4 minus 1. One, 2, 3. If L is 3, what are the possible values of m sub L? Remember, m sub L goes from negative L to positive L. So we'd have negative 3 all the way to positive 3, and fill in the numbers in between. Negative 2, negative 1, 0, 1, 2, 3. How many subshells are in the M shell? Remember, this refers to L. And M shell, that means N equals, go back up to our chart, M means N is 3. So if N is L, remember, goes from 0 to N minus 1. So L could be 0, 1, or 2. How many values are those? 3. The answer is 3. There's 3 subshells in the M shell. How many orbitals are there? So now again they're referring to m sub L values in the F subshell. Small cursive F, so that means little l has to be what? Go back up to our chart. Little l is 3. So m sub L goes from negative 3 all the way to positive 3. Negative 3, negative 2, negative 1, 0, 1, 2, 3. So how many orbitals are there? How many of these values are there? 7. Give notation using letter designation per L for the subshells denoted below. So let's remind ourselves, L could be 0, 1, 2, 3, 4, 5, 6. So what are the possible letters? S, P, D, F, G, H, I, and then it gets alphabetical after that. So if N is 3 and L is 2, that corresponds to D. So we'd have 3, D. N is 4, we'll have 4 and what letter? S. All right, because 0 is S. Here now we have 4, P. State which of the following sets of quantum numbers would be impossible for an electron in an atom. So remember, the idea behind quantum mechanics is that each electron has associated with it its own set of quantum numbers according to that table, right? Those rules have to be followed. So is there anything wrong with any of these sets of quantum numbers? Let's check them out. In the first one, can n be 2? Yeah, there's nothing wrong with n being 2. If n is 2, can L be 0? Well, let's remind ourselves, L goes from 0 to n minus 1. So yeah, there's nothing wrong with L being 0 if n is 2. Can m sub L be 0? Well, remind ourselves, m sub L goes from negative L to positive L. So there's nothing wrong with that. And m sub s can be a positive a half. That's good. So these are all okay. How about the next one? If n is 1, nothing wrong with that. Can L be 1? Nope. So impossible. We don't even have to keep going. Can n be 0? No. Remember, n is only positive whole numbers, not including 0. So that's impossible. Didn't even get started. Can n be 2? Nothing wrong with that. If n is 2, can L be 1? Sure. Can m sub L be negative 1? Yeah. So these are all okay. Can n be 2? Sure. L can be 1. M sub L can't be negative 2, though. So, impossible. So which ones are impossible? It was B, C, and E. What is the number of orbitals in each of the following subshells? So remember, this corresponds to m sub L. What are the different m sub L values we can have? And all that depended on was L. So in each of these cases, we got to figure out what L is. Well, 0, 1, 2, 3, 4, 5, 6. What were those letters? S, P, D, F, G, H, I. So if it's G, that means that L is 4. And if L is 4, m sub L goes from negative 4 all the way to positive 4. So negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. So that means 9 different values, 9 orbitals. It's F. That means L is 3. So that means we'll have 7 orbitals. S, that means L is 0. So we only have 1 orbital. Positive 0 to negative 0, just 0. P, that means L is 1. So we'll have 3 orbitals. Right? Negative 1, 0, 1. That's 3 numbers. List the possible subshells for the n equals 7 shell. Remember, subshells. So if n equals 7, what can L be? L can be 0 all the way up to n minus 1, 0 all the way up to 6. So 1, 2, 3, 4, 5, 6. So what were the letter designations again? S, P, D, F, G, H, I. So list out all the possible subshells. All we do is write 7 with each one of these. 7S, 7P, 7D, 7F, 7G, 7H, and 7I. There they are. Those are all the possible subshells for the n equals 7 shell. One of the major ideas behind quantum mechanics is that each electron has associated with it its own set of quantum numbers. And here they are. Just understand this table, and you can handle anything that the homework is going to throw at you. Good luck.